Am I audible? Am I audible?
Yes, sir.
Am I audible? Hello, am I audible?
Yes, sir.
Yeah. So today we will discuss about very important topic which is extensively used in embedded system applications related to motor control, related to automation, related to robotics. This block was not present in the traditional microcontrollers like 8051 provided by Intel. That is a basic microcontrollers. Now almost all the state-of-art microcontrollers provide this facility to support these types of applications. So what is that block? As already I've shown there. So this block is popularly called as a PWM block or PWM hardware module. So PWM generally was implemented in earlier microcontrollers, use a software program. So we write the software program and then we generate them. What is required? So the program was running continuously using the software timers, using the software delay programs or the hardware timers to generate the PWM waveforms. But having the PWM hardware itself in the microcontrollers have an advantage that you need not do much of the program continuously. That is, the microprocessor or the CPU core, what is present inside the controllers, need not run the program continuously. It need not be blocked. You just instruct the PWM hardware what is required for you, how many motors you want to control, or how many DC or servo motors you want to control, what is the speed of running. That's all. You have to just identify your requirement, just inform that hardware, and just you can focus on other work. So these hardware blocks will work independently as per the instructions given by the controller. This is an advantage of having PWM hardware built into the microcontrollers. So the software work or the software written by the programmer is also less. It's very simple to generate the different PWM waveforms. And it's also easier for the microcontroller to delegate this work to this module. So today we will learn about how the PWM block of any microcontroller, this is whatever I'm talking today, is applicable to any microcontroller. So, but our focus is on LPC2148. So we will discuss how the PWM modules are programmed and how we can realize the motor control using the PWM block. We have already learned a module called timer module, which is present inside the microcontrollers. The PWM module is just an extension of a timer module in the sense, whatever the registers we had in the timer module still present in the PWM module. Upon that, an abstraction layer is provided to make it configurable to more suitable for PWM operations. There is also another facility is also available. For example, for my project work, I don't require the PWM module. That is, the project work does not require the motor control. In such cases, what I can do is I can use the PWM module as a timer module. In such cases, it will be the third timer of the LPC2148. Already we have the two timers are there, timer 0 and timer 1. So if you want one extra timer, so you can always use the PWM itself, PWM module itself as a timer module. So when you can use that one, if you're not interested or not required in a product, the PWM operation. So PWM basically works as a timer. So we will learn that how exactly the extra features of PWM are implemented on the timer. Now, so LPC2148 provides one PWM module, but that PWM module is capable of generating 6 PWM channels. It's a PWM 0 to 5. So you can call it a PWM 1 to 6 or 6 PWM channels are available here. So these 6 PWM channels can connect it to 6 motor driving circuit to generate different motor waveforms. So now we will understand how this works. So these are the pins, PWM 1 to 6 are available outside the microcontroller chip. That means that these are the pins you have to use to connect to the motors, whatever the motors you're going to control. So these are used for that motor control. Now, these pins, as we already know that, are overlapped with the GPIO pins. So one basic requirement you have to always understand is whenever you are using PWM 1 to 6 pins, the corresponding GPIO pins functionality is not available. So what is the first thing you have to do it? For example, I am interested to control only one motor. Choose one of the pins, PWM 1 to 6, which is required. Configure them using the pin selection register to act as PWM 6. That is the first step you require to do in the program. So identifying how many motors you want to control, and then identify the pin number, which PWM you are going to use it, anything you can use it, and then configure them to work as a PWM using a proper pin selection registers. Now, what is basically a PWM waveform? So we know that any PWM waveform is basically, it's an on-off waveform. It's just a square waveform. It's not a square, it's a rectangular waveform. Just it can have only on and off, that's all, high or low. Each of the PWM waveform has got the two characteristics we generally call. The first character is called as pulse period is a one characteristic. The second character is called as a pulse width is a second characteristic. So what is the meaning of the pulse period and what is the meaning of a pulse width? Pulse period, as the name says, it is nothing but the total period of the one clock cycle. So that means that if I say on plus off, if I add together, so that will be the pulse period. So indirectly, the pulse period dictates the frequency of your waveform. So whenever you want to drive any motors, you should always see that the data manuals, you have to refer them, just find out what is the best frequencies the motor works. In certain frequencies, motors are not smooth running. So you have to identify for the type of motor you are developing or using in your project, what are the best frequencies. So that frequencies you have to design the T period. So the pulse period you have to design based on the requirement of the motor. Now that is called as a pulse period, on plus off. What is a pulse width? In a given period, how much time the waveform is on. So that is high voltage. That is called as a pulse width. So T on, we call it a T on. So generally, so if you take the ratio of on plus total period, so we call it as a generally duty cycle, because this duty cycle is effectively dictates what is the voltage I can generate at that particular pin. Because when we control the motors, class. ಏನು ಹೆಸರು ಅವನು ಡಿ ಇದು ಡ್ರಾಪ್ ಸೆಮಿಸ್ಟರ್ ರಿಪೀಟ್ ಮಾಡ್ತಾನೆ. So sorry, I'll continue. So duty cycle is basically so it's on plus on divided by T. So the overall duty cycle what we get is nothing but on plus T period. So if I multiply by 100, you'll get a duty cycle percentage. So this I can control using our LPC2148 PWM module. Let's understand how we can control these operations. Now, what are the extra registers required in a PWM module apart from the registers which is generally available in case of a timer module? Number one, you should have a facility to choose how many channels you require, and whichever the channels you require, only you have to enable that channel. And these PWM waveforms will be generally of two types. We call it a single edge PWM waveform or a double edge PWM waveform. What is the meaning of that? In a single edge, the moment the PWM waveform starts, always the output will be high. Only I'm controlling the falling edge of my waveform. That means that the moment I start the waveform, it will be always high. Only when it has to fall, when it has to become zero, I'm controlling through the program. That is how much of time this has to be on. So that is the only thing I'm controlling it. So this is called a single edge PWM waveform. There is what is called double edge PWM waveforms are there. That means that if this is the T time, total time is available, let's say T, I can control when it will reach from 0 to 1. I can also control when it has to reach from 1 to 0. That means that both the rising edge I can control, and also I can able to control what is called as a falling edge in a given T period. So these are called as double edge PWM waveform for a finer control. So people use this double edge also. For our discussion and syllabus, we restrict our discussion to a single edge PWM waveform. So there is a facility is available. There is a facility is available. So using that, I can able to program whether these PWM channels are enabled or disabled. And also, I should also have a facility to configure each of these channels as single edge or a double edge. Now, so to configure this as single edge, double edge, and enable this PWM channel, a register is provided. So separately, it's called the PWM control register. So all the registers in a PWM block or start with the name called PWM TC, PWM MR0 like that. So all the registers will be prefixed by the PWM. So PWM PCR is a PWM control register which you use to selectively enable the required PWM channels and to configure the PWM channels as a single edge or a double edge PWM waveform. So that is the purpose of this one. So here the bits are provided here to configure that one. So since by default, if I don't do anything on reset, all the channels are single edge. So I'm not worried about which bits are used to control the single edge or a double edge. So I'm only interested in this register what bits, the bits corresponding to these register, these channels. So only those bits I'll be able to set that. Whenever you set that particular bit, it will become enabled. If you don't do anything, it will be disabled. By default, all the channels are disabled. You have to explicitly make corresponding bits in this register 1 to enable, selectively enable these channels. Now, having understood this one, now we'll move to the other extra registers which are provided in the PWM channel, in the PWM module to make it work as a PWM, to make it generate PWM waveforms. What are the other things? Now, the MR0 and MR1216, there are more number of registers are provided here. There we have only MR4 match registers were there in the timer. They have provided more number of match registers. What is the purpose of it? How it will be useful? The moment if you look at any PWM waveform, as we know that, correct now. So there are two things I have to configure, as I said earlier. One is the pulse period and the what is called as the pulse width I have to configure. That means that the rate at which this waveform generates, I have to control it. Now, so there is a one assumption they made in the LPC2148 module to make the hardware simple, but also the programming also simple. All the PWM waveforms, whatever they have provided in 1 to 6, will have the same pulse width. In the sense, pulse, the rate will be same thing. So the pulse period or the pulse rate will be the same for all the. For example, if the frequency of the PWM is 1 kilohertz, that means that the frequency of all the PWM waveforms should be 1 kilohertz only. You cannot change it. That means that the pulse period or the pulse rate is the same for all those things. Now, to make hardware simple, they have provided this facility. But what I can change it, the pulse on time I can change it. So the pulse width I can change it. For example, So I can generate here 1 kilohertz of duty cycle 10%. So I can generate PWM waveform on a PWM6 with a duty cycle of 90%. So the duty cycle percentage can be changed for all these PWM channels, but only thing is the pulse rate or pulse period, the frequency of the waveform will be same thing. So that means that I can have 1 kilohertz waveform under all the channels, but each of the 1 kilohertz channels can be having a different duty cycle. Effectively, the DC voltages what is produced on the 6 is variable because why? There is a facility to change the pulse width. So that is how it is done. Now, since all of this have the same pulse rate, there should be a facility for me as a programmer to decide what is the frequency of this waveform I should generate. As I said, the frequency is not a fixed set. It depends upon the motors you're going to control. Some works better at 1 kilohertz, some better at maybe 2-3 kilohertz, like that. You have to refer the manual of the motors. So they have provided a register where I can indicate what is my pulse rate or the pulse period. That register is called the MR0 register. Now, how does the MR0 register can control the pulse rate? It is in terms of the peak clock. Because any clock, basic building block of any module, if the clock is dependent, that means that who provides the clock for that? Peak clock provides for that. So peak clock decides how many clocks will constitute one T period. For example, if I say that 1000 T clocks is required for the T, I should load into the MR0 register 1000. So if I load 1000 here, it is understood that what is the total time period of one clock cycle? It is 1000 into peak clock. So whatever the value I'm writing into the MR0 register will decide the total T of the pulse width PWM waveform. So MR0 decides now. So MR0, whatever the value you load, that into the time period of one peak clock will be the total time period of the one PWM waveform in the LPC2148 module. Now let's understand now how do we control the pulse, the width. The pulse width again is measured in terms of what? Number of peak clocks. Because what is the measurement unit? Number of peak clocks. 1000 with 1000 peak clocks, like that. How many peak clocks will constitute the pulse width? That will be controlled by the 6 match registers MR1 to MR6. So which in turn control all these PWM channels. So if I want, for example, 50% duty cycle, then what should I load into the MR1? I will load into the MR1, so 500, because I already loaded 1000 here. I will load 500 here. Then what will happen? Whatever the waveform you get here will be the 50% duty cycle. If, for example, MR1, I want 10% duty cycle, what do I load? Since the 1000 is already there, so I will load 100 here. So 100 by 1000, that is a 10% I'm going to get. So that means that whatever the value you're going to load into MR1, MR2, should range from where? From 0 to 1000. It should not exceed the value you are loading into MR1, MR6 should not exceed the value what is present in MR0. So it should be in this range. So whenever you are putting the value MR1 to MR6, based on the what value you are putting, take the ratio between this one. That is whatever the value you put in MR1 to MR6 divided by 100 into 100 gives the duty cycle. Like that, you can able to control the duty cycle or the PWM waveforms you can able to generate. That is why it's so easy for the programmer. He did not write any program at all to generate a PWM waveform. What do you write? Just decide how much of speed you want or how much of duty cycle you require. Just that much values you load it. Always you can make this as a constant value because it's not going to change for a given motor. So only these things you can keep changing. By changing this value, what will happen? You can rotate the motors at different speeds. Just change the value here, the motors will rotate. Once you write into this one, correct now, the programmer is free. The CPU core is free. This block itself is capable of making the motor rotating continuously. So that means that the microcontroller, whatever the microcontroller, the core we are using, just delegate the work. For example, what is the speed you require? I want this motor to work at 500 RPM, other motor to work at 1000 RPM, other motor to 15,000. Just load the proper value into the MR1 and just leave that. That's all. The microcontroller is able to do other work. That is the beauty of these modules, what is present inside the microcontroller. Now, what is the function of other registers? Other registers, there is the same meaning as in case of a timer. For example, timer counter is the one which decides how much of time is elapsed. This can be a software programmable. So as we had a timer control register in case of a timer, here we call that register as a PWM timer control register. Using this register, there is a bit is provided in the D0 bit. By writing 1, you can start the PWM waveform, that is timer counter will be enabled. By writing 0, you can stop the PWM counting. So this is used to switch on and off the timer counter. So this register. So there is one more bit is provided in the PWM TCR register. So that is second bit, as we know that the second bit is nothing but the reset. This is similar meaning as timer counter, timer registers. So by writing 1, what will happen? You can reset the contents of the timer counter value. So there is a third bit, one more bit we are using here. That's a third bit. So this will be the first bit. So this will be the second bit to reset that. And there's a third bit is available. This bit is important. So this bit, it decides whether you're using the whole of this module as a timer or a PWM module. So this bit was not there in the timer because timer module always works as a timer. Whereas here, this bit enables whether you're using this block as a timer module or a PWM module. You have to write into the third bit, D0, D1, D2, D3. So D3 bit you have to write into 1. The moment you write into this bit 1, so what will happen is the PWM module is enabled. So then only the PWM logic will work. So it's very important to write 1 into the third bit so that PWM module will start working as a PWM module. Now, so the prescaler, same thing, meaning it further divides the peak clock so that accuracy or more delay you can able to produce. So that's an advantage of a prescaler. If you don't do program, prescaler is disabled. Peak clock is now directly connected to timer counter. Now, PWM MCR, this is not used in the PWM as the meaning of the mode control register or match control register will be the same as timers. So this is used to only when this PWM module uses a timer to decide whether after the match is reached, whether you have to reset, whether you have to stop or to generate an interrupt. Same meaning will be carried. This is used only when you use this module as a timer. Now, as a programmer, what are the things I have to do now? So first of all, I have to do what? I should be able to enable the required channels. So I have to control the single edge or a double edge. So I will do that using this register. Then I decide what is the frequency of the motor, which I'm going to control. That value into the peak clock I'll decide and load into the MR0 value. Then what is the duty cycle required? I load into these registers, and then I start the timer counter by enabling the PWM module. It starts working. So this is how we will program the PWM, the module. There's a one concept is available here in the case of a PWM module. So it is called as the shadow registers. Because what is the concept of a shadow registers? That means that whenever let's say you're running the motor is running at a particular speed. Let's say it's working at 500 RPM. In between, you receive the instruction from the user, change the motor speed to 300 RPM. So the PWM waveform is going on, still it's not completed. That is it is in between it's between the one clock cycle. Somewhere the programmer wants to instruct here because he wants to change the speed. So you should complete the cycle and then only you can start the next one. So that is why they have provided what is called shadow registers for all the MR1 to MR6, shadow registers for all these things. So what is the meaning of a shadow register? That means that as soon as you write in, the programmer writes into this one, it will not go to this register directly. It will be turned into the shadow registers first. So then only after the one cycle is completed, then the shadow registers data will be copied into the MR1 to MR6 one. So how does that? The PWM module knows that shadow register things to be copied to here? Because shadow registers are there for MR1 to MR6. Does all the shadow registers to be copied to MR1 to MR6, or only one of the MR1 to MR6 shadow registers to be copied to MR1 to MR6? So that is why they have provided one more register called latch enable register. That means that so which of the shadow registers will be copied to this one, that will be decided by one more register. It's called as PWM latch enable register. So this register decides which of the contents of the shadow register which is written by the programmer will be copied. Shadow register will not have a different name. That means that whatever you write into the match register, that will automatically go to the shadow register in the PWM module. So only thing is, by enabling this proper bits in the latch enable register, the contents of the shadow register will be copied here. For example, I want to, I'm using the PWM 2 channel. So that which is a register which is important for me, MR2 is important for me. So that means that, so as soon as you write the new data into MR2 register, please write the one into the corresponding bit of the latch enable register. The moment you write 1 here to this bit, so after the clock cycle is completed, the PWM module checks in this register. Which are the bits is 1, only for those bits, the shadow register contents, which is already written by the programmer, will be copied to the corresponding match register. So this is another thing you have to do, keep in mind when you do the programming. Now, So now we will start. This is an example of how the PWM waveform for a particular channel called PWM5. For example, so in this example, we are given the 100 as a total T. 100 peak clocks is the total T of the PWM for this waveform. 65 we have written for MR5. That means that on time will be 65 peak clocks. So the total period will be 100 peak clocks. On time will be 65 peak clocks. So this is how we will able to do this one. So now we will start writing one program and understand how PWM can be programmed, module can be programmed. Now, so let's take any one of the channels. I said the PWMs are already combined with what other units. For example, if you look at the here PWM6, it has been overlapped with what P0.9. So like this, you have to find out so which of the PWM you are going to use and use a pin selection register to configure that one. Since we have discussed that pin selection register many of the times, just make sure that you have to use the pin selection register to use any of the PWM channels. So, for example, PWM3, look at the P0.1 is enabled using a PWM3. So if you want to use a PWM3, you have to configure the P0.1 pin using a pin selection register to act as so alternate function 2. So function 0, function 1, function 2. You have to write into the proper register. So now let's start writing the program. Now we will write a program to generate a PWM waveform. So I will use PWM channel 3. This can be anything. I am giving a PWM channel 3. So I have written a function called PWM Unit. By the moment I call this function, I said now, with all the settings, what is required for the PWM channel thing is done in this function. Now, what does I do in the main program? In the main program, I'll only keep changing what is the duty cycle I required so that I can able to produce the different varying voltages, which through that I can able to control the speed of a motor. So now, for example, say here I written 500 because I have written into the MR0 1000. So that means that any value I can write from 0 to 1000 into this MR3. So let us understand first what is PWM unit I have written, and then we'll come back to this function. Now, this is a PWM unit. So this as a set for identified. Now PWM3 channel I'm using it. I'm writing a proper value to pin selection register to use the PWM3 channel. So act as PWM3 channel. So that is so in the pin selection register in the proper bit position I've written it. This we have done it many number of times. Let's not concentrate on this one. Let's go to this one. Now, PWM MR0 register, I should indicate what is the pulse rate, what is the frequency of the waveform you're going to generate. And you can take any value as such. Only thing is, if you are very clear what is the wave frequency required, you set for that. So since it's a lab program, I've just taken some random value. How much I've taken? I have 2000. Anything you can take it. So any other value I could have taken here. So I have taken it 2000. So that means that what is now one pulse period? Now the pulse period becomes what? The total period pulse period will be nothing but so 2000 into the time period of 1 peak clock. So 2000 into 1 peak clock. So if say 15 megahertz is my the peak clock waveform, that is so 15 megahertz means 0.067 microseconds. So this is the time period of your PWM waveform. So that's what it decides now. Now I want to select the channel 3. I said it is not possible to use the PWM set because all are disabled. You should enable that one. So that we can do is using what is called PWM control register. So in this control register, the bit D3 to select the single edge. So since it's all by single edge, so I'm not configuring for single edge and double edge because it by default is single edge. The only thing what I have to configure is, so I have to configure, so the PWM channel 3 should be enabled. So what are the registers for that? So you can just look at the register PWM. Let's look at the PWM control register, PCR. So if you look at the PWM control register, so what are the lines? So bits D9 to D14 are used to enable the channels PWM1 to 16. Now D9 bit controls the PWM1, D10 PWM2, D11 PWM3. Since I am interested in PWM3 in my example, so I am just configuring that bit. So D11 bit, I am making it 1. So how do you make a D11 bit? See that here 100. That means that so the D, when I make it 8 here, it's nothing but what? D11 bit. D11 bit becomes 1. So by writing this 1 into the PWM control register, I am enabling PWM3 channel. So this is the only thing you have to do it. Always remember that So D9 to D14 are the bits are used in the PWM PCR register to select the which of the PWM channels you require. So I've done this job. Now I've enabled the pin to work as PWM. Then I've selectively enabled the PWM channel 3 to start working. Now, so I've already written 2000 into the PWM MR0 now start the PWM module. How do you start the PWM module? I said two bits are there, which is very important, these bits. So what are the bits? So one is you have to make the D3 bit, that is D3 bit in the PWM timer control register 1. So this bit was not there in the timers. So this bit is provided only in case of PWM module. Otherwise, all the bits are similar to the timer control register of a timers also. So this bit you have to make it 1. Whenever I make it, this bit is equal to 1. That means PWM module starts working. It becomes a PWM module. Otherwise, if you don't write it, it works as a timer module. And then write 1 into this one. So PWM starts working it. So writing 1 means start the PWM timer counter counting. So now I've done that one. So what is that I've done? So I've enabled those two bits. So D3 I made it 1 and the D0 is equal to 1. So that is why you got 9. So 9 means so 0 0 0 1, correct? Now this is the D0 bit and this is a D3 bit. So now this is all what is required for a PWM module. This is written only one time in the project in the beginning of that program. Yes or no? So the 4 things which is required for a PWM programming, I have finished it now. So selected the pin and work as a PWM pin, then selectively enabled which of the channel I required it and selected the single edge. By default it's there already. Then the pulse rate I have decided based on the motor I'm going to drive it. Then enable the PWM module and start the PWM waveforms to be generated. So after this is done, now your programming starts here. So what is the programming here? You can decide what is the duty cycle or the speed at which you want to rotate your motor. I just taken randomly to rotate the motor at 50% duty cycle. Since I already loaded 2000 into the MR0, so I wanted to run this at a 25% duty cycle. So since I already taken 2000 in MR0, if I load 500 by 2000 becomes what? 25%. So I've loaded here. And I said that whatever you write in the PWM registers, this value do not go into the MR3 register. It will go to a shadow register and will be waiting for the PWM module to copy from the shadow register to this register. To make that happen, you should enable the corresponding bit required for this to be 1. Since I'm using PWM 3, so 0 1 2 3, that is a third bit. You can just see that. So these are the bits I've just enabled. So I'm using PWM 3. So that means that this is the bit. So this bit I have to make it 1. So 1 0 0, that is 8. So that is why I'm writing a 0 8 here. So this will copy. So in the next clock cycle, after the clock cycle is completed, in the next match, when the next match event happens, then this 500 will be copied from a shadow register to MR3, and the new waveform with a new duty cycle will start generating it. So this is how you can program the PWM module of LPC2148. Now let's understand that we will take on product development, small product we develop now. So using this PWM module now. So these are some of the calculations. So if, for example, P clock is 15 megahertz, T is 0.067 microseconds. Pulse rate is nothing but is what? T on plus half. This is 2000 into T. So what is the pulse width? Because I given a 500 to T. So this is a value and the duty cycle is 25%. So now we will start building a small product where I'll be controlling the DC motor speed. Let's understand how the DC motor works. I'm audible? I'm audible?
Yes, sir.
Yes, sir.
Yeah. So what is a DC motor? DC motor is completely different from your stepper motor. Stepper motor is called as a digitally controlled motors. Digitally controlled means every step is to be initiated only by the digital sequence. If I don't give a digital sequence, it will never go to the next step. Yes or no? That is a stepper motor. But you cannot use the stepper motor for all application because the cost is more and it may not be required. You may not run at very higher speeds like a DC motor. So it depends upon the requirement of your project. Yes or no? You have to choose whether you have to use a stepper motor or a DC motor. So whenever each of these motors finds number of applications, both are different. So you cannot use a stepper motor where DC motor is suited. For example, the fan, the cooling of a CPU, on the motherboard, they're all DC motors used. You cannot use a stepper motor for that purpose. So how does a DC motor works? All the DC motors will have just only 2 wires, unlike the 5 or 6 wires what you have in the stepper motor. Because in a stepper motor, you require a 5 or 6 wire because you have to push the digital sequence into that. In case of DC motor, there's no digital sequence is required. You require just a voltage. So that is why they provided just a 2-terminal, like it's like any other DC device they are provided here. So the moment you connect the voltage, which is being designed for that DC motor is designed. When you go to the market and ask DC motor, the first question they ask is what voltage you require or what is the torque you require. The more the torque you require, the more the weight or the load you want to drive it. So you have to take a DC motor of higher capability. So whenever you take a DC motor of higher capability, so different DC motors available, 12 volts DC motors available, 24 volts available, 48 volts is available. Even in a given voltage, so the ampere rating will be different. So if the 2 amps, it can able to drive the more load. If it's a 4 amps, it can drive a little more load. If it's a normal DC motors, which used in a toys, very minimal in terms of milliamperes, the current will be required. So you have to always find out what is the load or the torque I required in my project. Based on that, you have to choose the DC motor and you have to choose the ratings for that. Now, so understanding that DC voltage, where do you get the DC voltage? You can use an adapters or you can use a battery. So depends upon if it's a very minimal voltage, you can use a battery. If a larger voltage required, always you have to go for a other power supply. Either you can generate you can use a solar panels. From that you can generate the voltage. You can drive the battery. From that you can supply, or you can use it directly. Adapters, you can use it. Now let's consider for the next 10 minutes of discussion that I'm using a DC motor which will be operating at a 12 volts operation. Now, if I give a 12 volts directly to these 2 pins, motor starts working at the rated RPM. Now, it started rotating in a particular direction. It's, let's say, clockwise, it started rotating it. Now, what is the only thing I can change for this motor? Immediately, the things I can change, I can replace plus and minus. Instead of minus plus, I can give the plus and minus this side. The moment I change the direction of the power supply, then what will happen is the motor starts rotating in other direction. So that means that by reversing the polarity of the supply, I can change the direction of the motor either in the clockwise or a anti-clockwise. So what else I can able to change and control the motor? One is the speed of the DC motor, you can change it. How do you change the speed of a DC motor? By giving a voltage, variable voltage to this point. What is the rated voltage? Rated voltage is 12 volts. That means that there is a facility for me to vary from 0 to 12 volts. If I bring it to 0 voltage, motor stops rotating. If I put it to 3 voltage, motor starts rotating at particular RPM. If I supply the 6 voltage, it increases. If I give the 12 volts, it reaches to the peak. That means that by varying the voltage supply to the motor, you can make the motor run at a different speeds now. Now, how do you, because all the controllers are digital systems. Now, how do you vary, how do you generate these DC voltages? You may ask the question, sir, can I use a DAC? DACs are generally not used for this type of motor driving applications. DACs are generally used for producing the sound, yes or no, playing the music files and all those things. We use a DAC. So for a motor control, industry uses, because you require a lot of power to drive for that one, you cannot use the DAC is not generally used. So PWM waveforms are extensively used in the industry to arrive at variable DC voltage, which is required to control the speed of a DC motors. Now, how do you get a variable DC voltage? So what is the formula? We know that. So given the PWM waveform, if you take the formula and just add the supply voltage for that. So we know that already the duty cycle formula is on by T into, now I'm adding one more factor. What is that? Supply voltage. So if you connect what is the maximum supply voltage you are supplying to the motor through a adapter, that you write it. So that will be this one. That means that when completely on, when your waveform is completely on, there's no off is there, then it runs at what speed? 12 volts. That is the full power, 12 volts. If it's completely on is nothing but off. If T on is equal to T by 2, that means that 50% of the duty cycle. In that case, what is, you are supplying half the power. So that means that by varying the duty cycle, you can produce a 0 to 12 volts voltage at the terminals of the motor and make it work at a different speeds. This is a principle of DC motor control. Now we will see that how I can design a circuit to make the DC motors work. So as we already know that the microcontrollers cannot be directly used to drive the DC motors. What is the one method? If I am interested to run the motor in only one single direction, I can use one transistor and I can drive the transistor using P0.2. Opto-isolator can be used or may not require, depends upon your requirement, or I can directly connect this to here also. So by driving the transistor, I can make the motor carry the required current or not. So that is a possible. It's a one direction. But whenever the motor requires to run in two directions, the popular what is called as H-bridge configuration is extensively used in the industry. This H bridge looks like an H shape. If you consider the power supply and the switches, they look like and the motor, it looks like a H circuit, H shape. That is why it's called as a H bridge circuit. How does the H bridge work? The load, that is a motor, is connected in this configuration, and the power supply to the motor is provided at this place. So this one, let's understand now. The H bridge configuration is designed to make the motor rotate in two different directions and at different speeds. Now, here there's only one switch I have used. One transistor is required when I'm required to run the motor in only one direction. Whenever I'm required to run the motor in two different directions, I require four switches. I require four transistor switches. So switch 1, 2, 3. If I want to rotate in a clockwise direction, what should I do it? I should switch on the switch 1 and then switch 4. Then what will happen? The current flows in this direction. It rotates in a clockwise, and switch off this two switches. Whenever I want to make the motor rotates in the anti-clockwise direction, so I'll switch on the switch 2 and then the switch 3. Then the current flows in the other direction and motor rotates in the anti-clockwise direction. So whenever you want to implement an H bridge circuit, you always require from microcontroller how many inputs. So sorry, how many outputs? 4 outputs are required. Each output is going to control one switch. Now, so generally, so to design one H bridge circuit using the 4 transistors, when putting a lot of resistors there and using the 4 pins of a microcontroller, it's a big hardware circuit. So what industry does is they provide these H bridge circuits in a single IC. So it is very easy to use those motor driver ICs and implement in the project. So what are that mean that all of this circuit is provided in a single IC, and also they have reduced the number of pins also by abstracting the selection of based on selection of these bit switches internally itself. In the sense, you tell to from the microcontroller, just say that I want clockwise direction. Then automatically they will only selectively switch on the switches. If I say microcontroller, I want an anti-clockwise, then automatically the corresponding switches will be selected and the other switches will be disabled. That means that all this will be done automatically inside built-in ICs. So all these circuits are built into the ICs, and it's available popularly as a motor driver ICs. So what are those ICs? So the number of ICs available. So you would have studied probably in the Arduino when you use L298 is one of the popular motor driver IC available in the market. So we have used one more industrial grade driver IC called DRV8801. DRV8801 is like an L298 only. It's one of the popular motor driver IC which is used in the industry. Now, so any of these ICs you take, either 298 you take it or 8801, all these DC motor driver ICs will be work in the same fashion. No changes are there. Sometimes what will happen when you go to the SP road or order online, you get a small boards, motor driver boards. These boards in turn inside uses these ICs and they build the circuits around it and gives the proper pinouts to make the connections. Now, since we are building a product on our own, including the microcontroller, I'm just taking the IC to build IC inside my circuit. So what are the pins provided in this IC? In this IC, there are 3 sets of connections you have to make it. Number 1, first of all, identify what is the voltage of a DC motor it runs, whatever the motor you purchase in the market. Connect the power supply, that is adapter supply, to these 2 pins. One is to the 12 volts, other to the ground in this case. Then identify the 2 pins what is provided in the driver IC, which is to be connected to the 2 pins of the motor. They will be named as out plus and out minus. So I've connected out plus here and out minus here. Now the power required for this motor is being supplied here. The power required for this is being supplied to this one. Now what does this microcontroller do? Microcontroller now controls how much of power is to be supplied from this adapter to this motor. See that this is not directly connected. In between, this IC is used, which is controlled by the motor, which decides how much of power to 12 volts, that is 0 to 12, I should supply to this motor to make the motor runs at a different speeds. So what are the pins provided by this IC? These ICs generally provide only 2 pins. As I said, inside all the logics has been implemented. One pin is called as a direction pin, which decides whether you want to rotate the motor in a clockwise or anti-clockwise. So if I tell just 0, the motor rotates in a clockwise direction. If I just supply 1 here, the motor rotates in the anti-clockwise. It may be any other, either 0 means clock, other anti-clockwise, or it may be other way also. You just refer the data sheet of this IC. So one pin is used to control the direction. What is the other pin? So other pin of this IC, which is the one very important one, this pin decides what speed your motor should run. So as I said, what is the method? Method is a PWM waveform. So the PWM input is the other input pin of this IC, which will be connected to the PWM pin of the microcontrollers. So in this case, I just given a PWM6, I have taken it. So PWM6 is derived at the pin number called P0.9. I have connected here. So by writing a small program now in the LPC2148, as we discussed earlier, you can generate a PWM waveforms with a different duty cycles to derive the different speeds of the DC motor. See that now the interfacing is completed, and also we understood the program also. So now we'll build a small project. Now. Let's say I want to control the speed of a DC motor based on the let's say a temperature. I want to build a small project. I want to control the speed of a DC motor using the based on the temperature. Now, so what I have to do it, as already I know that this side programming we already learned it. Yes or no? By supplying the proper value to the MR6 register, I can able to rotate the motor at required speeds. Now, only thing when I require to base this speed on some other thing is what, on the sensor, like a temperature sensor, I have to connect both the modules into the program. So let's learn that how we have done that. So I've developed a small function. You can do it in a different ways on yourself. So run DC motor is a function. So where I've used two arguments in this function. The first argument specifies whether I want a clockwise or anti-clockwise. One means clockwise, two means anti-clockwise. So this, the second argument is I'm just varying from 0 to 100, which says that, so what is the duty cycle of the waveform I want to generate? In turn, this is nothing but what? I'm controlling the 0 to 100% speed of the motor. 0 means, so motor stops. 100 means highest speed it's running. So the second argument controls the speed of the motor. Now, that's all one statement I given, just run DC motor, stops. So the programmer need not do that. In the sense, the code need not do any other work. You just write the statement and just you settle here. Because why? The PWM module works independently. It does not require the core intervention in between. Now, we'll see that how I written the run DC motor. So run DC motor is a direct program, just specifying it. So what is the direction? If the direction is 1, I'm just setting that bit is equal to 1, and otherwise I'm clearing the bit. Why I've set? Because I've used the P0.28 here. So P0.28, these are the same pins we have used in the lab also, the lab kit also. That is why we have taken the same pins. So P0.28 is a pin through it's a GPIO pin, which is going to control whether the direction of the motor is to be clockwise or anti-clockwise. So if it is a 1, I'm just setting that bit, otherwise I'm clearing the bit. It's the first job, that is setting the direction. So second one, after setting the direction, I have to set the speed of the motor. That's the duty cycle percentage. So as I said, the MR0, what is the value loading at MR0? It can be anything, you can assume it. So if you're running the DC motor, just check that what is the speed frequency at which your DC motor has to run. So here I've chosen 1000 as a value, because that controls the motors what we use in the lab, small motors, to run properly. So I've just taken 1000 now. So this is just a small formula here. If it's a 100% duty cycle, then 100% duty cycle, then what will MR6 value? So MR6 will be 1000 only. That means that, so if you load MR6 same as the MR0, it will be 100%. The motor rotates at the highest speed. If you give any other value here, using this formula, you're loading a value which varies from 0 to 1000. So I'm just bringing down the value. 0 to 100 is what I'm specifying here, 0 to 100. So that 0 to 100, I'm just bringing to a value in the range of 0 to 1000. I'm putting that into MR6. Then, so this is for a PCR. We have seen that. Enable the PWM6 channel, because I'm using PWM6 here. So then, as we already learned, so enable the PWM module and start the timer. So this is the new value. What are the values you're supposed to load into PWM6? Since for PWM6, so this corresponding bit is bit on to copy the data from a shadow register to the corresponding MR6 register. So now, so the run DC motor, the moment I call this this function, then the motor runs at a particular speed, so in a particular direction. So only assumption I made is what? P0.28 I've used as a GPIO pin to control the direction. P0.9 PWM6 is a channel I've used to generate the waveform. So with this assumption, this program has been written. Now, so can we integrate this with a sensor? Now, how do we integrate with a sensor? So already we have discussed how do we program the ADC module, and also it has been discussed in the notes how there's a function called ADC. So this ADC function is used to read the data, digital data from a sensor connected to the ADC. So we know that if 1 means it's ADC 1, we can just check that. You can either this first parameter decides which ADC you are using it. The second parameter is which ADC input you're using the particular selected ADC. So now by using this ADC function, we can read the data coming from the particular sensor, which is connected to the corresponding input of the ADC module. So then I'll get a digital value. We know that this value varies from 0 to 1024. Since in this function, this value is only from 0 to 100, I'm just dividing arbitrarily by 10. So if I arbitrarily divide by 10, so 0 to 1023 will come into the range of 0 to 100 approximately. If it exceeds 100, I'm just writing 100. This is a small map function, so which is written in a Arduino board, which is available. You can write your own map function to do this conversion. So whatever the sensor value, digital value I'm getting it, I'm just bringing it the range of 0 to 100. Then I'm just calling the run DC motor function with that digital value 0 to 100. And then this program runs in a continuous loop. Then as the temperature increases, the motor speed increases. As the temperature comes down, the motor speed also comes down. So like that, you can able to integrate a sensor into a motor. So and completely build the project. So this is one of the experiment in the lab. So today in the lab, you're going to do this experiment. You have to demonstrate in the analyzer. So when you come to the lab in the college, so you're going to conduct this experiment by connecting the sensors and all those things. So this completes discussion on the PWM module, how to program the PWM module, how to build the products using the PWM module, and how the DC motor speed can be controlled using the PWM module. So I'll just stop. Stop sharing. Any doubt is there, you can just raise it out.